We can start taking derivatives of trig functions by building a foundation with the derivatives of sine and cosine x. We have that the derivative of sine x equals cosine x. We can see this graphically by looking at the graph of sine and cosine x, and remembering that when we take a derivative of a function, we get a function that tells us the rate of change, the slope, of the original function at any point. And if we look at sine x, and we think about its rate of change, when the rate of change of sine x is 0, it's at this point here, at this peak. The rate of change of sine x is no longer increasing, and it's not yet decreasing. If we look at the value of the cosine function at that same point, we see that the value of cosine x is 0 at that point. If we look at another point where the rate of change of sine x equals 0, which would be this point here, we can see that the value of cosine x is 0 at that point. And with those observations, we can hypothesize that the rate of change of sine x is equal to the value of cosine x. And that does prove to be true. So the derivative of sine x, the rate of change of sine x, is equal to the value of cosine x. So the derivative of sine x is equal to cosine x. And the derivative of cosine x is not just equal to sine x, it's actually negative sine x. And then the derivative of negative sine x is equal to negative cosine x. And if we wanted to take a derivative of negative cosine x, we would be back at sine x. An easy way to remember the derivatives of sine and cosine x is to picture this order. We have sine x, and the derivative of sine x equals cosine. The derivative of cosine equals negative sine x. The derivative of negative sine x equals negative cosine. The derivative of negative cosine x brings us all the way back to sine x. If we want to take the derivative of sine x, we know that it equals cosine x. But with trig functions, we have a function inside of a function. We have our x, and then we have sine of x, which is a function in of itself. And the chain rule taught us when we have a function inside of a function, we take derivatives of them both. So when we take the derivative of sine x, we're not just taking the derivative of sine, which is cosine, we're also taking the derivative of the function inside of sine x, which in this case is just x. And we know the derivative of x with respect to x is equal to 1. So when we take the derivative of sine of x, we have cosine of our inside function multiplied by the derivative of our inside function, which in this case is just 1. So it would be cosine of x times 1, or just cosine of x. With that chain rule in mind, we can take derivatives of functions like cosine of 5x. When we take the derivative of cosine, we know that it's going to be negative sine of our inside function, but then we take a derivative of the inside function. And that simplifies to negative 5 sine of 5x. With our order of derivatives on the left here, and with remembering that we have to take a chain rule of the inside, try taking a derivative of sine 7x. To do this, we know that the derivative of sine, if we look at our table on the left, we know that the derivative of sine is cosine. And then we have our inside function, which we bring down, and then we multiply by the derivative of the inside function. We know that this is a constant rule, so if we pull the constant out, and then we multiply by the derivative of x. We have x to the 1 minus 1, which equals x to the 0, which is just 1. So 7 times 1, 7. So we have cosine 7x times 7. I'm going to put the 7 in the front. What if we have something a little more complicated, like negative cosine 8 times x cubed? Well, we know by looking at our table that the derivative of negative cosine x is sine x, but what I'm going to do is to just pull the negative out in front, just to prove that that works. So then we have cosine 8x cubed without the negative. So then we have negative times the derivative of cosine, which we know is negative sine of our inside function. And then we're not done because we take a derivative of the inside function. So we're going to pull the 8, the constant 8 out front, and then we have the derivative of x cubed. The 3 comes down, and then we have 3 minus 1, so x to the 3 minus 1, which is 2. 8 times 3 is 24, so we have 24x squared. So back over here, we tack on 24x squared. Now if we distribute this negative sign and move this 24x squared out to the front, we have 24x squared sine 8x cubed. Now in the beginning, we knew that negative cosine x is equal to sine, and we can see that that holds up. What if we have a function like sine squared 2x? Well, sine squared is the same thing as sine squared 2x squared. In order to take the derivative of this function, we're going to have to use the chain rule over the sine 2x, and that would look like this. We bring down 2, keep the inside the same, sine 2x, and then we're basically doing a power rule over this whole thing, so we have 2 minus 1, which is just 1. That was just the first step in the chain rule. Now we can take the derivative of sine, which we know the derivative of sine is cosine, and then we have our inside, 2x. So now we have one more part of the chain rule, which is the derivative of 2x, which is just 2. So we had to do the chain rule 3 times here. We had the sine 2x squared, so we took the derivative of that by following a power rule, and then we took the derivative of sine 2x, which is cosine 2x, and then the derivative of 2x, which is 2. And if we simplify this, 4 sine 2x cosine 2x. If we wanted to take the derivative of y equals cosine of 5x times sine of 5x, we would have to recognize that we have a function times another function. And when you're taking a derivative of a function times another function, you need to use the product rule. And if you don't know how to do the product rule, you can check out my previous video where I go over the product, quotient, and the chain rule. So to take this derivative, we need to follow the product rule. To follow our product rule, we simply have to follow the derivative of the first times the second plus the derivative of the second times the first. In this case, f of x is our first, our cosine, and g of x is our second, our sine. So if we want to take a derivative of both sides, we have dy dx equals the derivative of cosine 5x times sine 5x. The derivative of cosine 5x times sine 5x. So following the product rule, that equals the derivative of our first, cosine of 5x. So the derivative of cosine of 5x, we know, is negative sine 5x times the derivative of the inside, which is just 5. And looking back at the formula for our product rule, that is all multiplied by the second, by our sine of 5x. So that was the first half of our product rule. And then we have a plus the derivative of our second times the first. So now we're taking the derivative of sine of 5x. The derivative of sine, we know, is cosine. And then we have our inside, 5x. And then multiplied by the derivative of our inside, which is 5. And that whole thing is multiplied by our first term, our cosine of 5x. So that was the second half of our product rule formula. Now we can simplify this. We have a negative and a 5 here that we can pull in the front. And then we have sine of 5x times sine of 5x. So that's sine squared of 5x. And we have plus. We can bring this 5 out front. And we have cosine of 5x times cosine of 5x. So that's cosine squared of 5x. We can do a little bit of fancy algebra and pull out the 5 and have cosine squared 5x minus sine squared 5x. What if we wanted to take the derivative of tangent of x? Well, this goes back to why we started with derivatives of sine and cosine, because using our trig identities, we can write tangent x as sine x over cosine x. We don't know how to take the derivative of tangent x, but we know how to take a derivative of sine x and cosine x. So if we rewrite this as the derivative of sine x over cosine x, we know that we can take this derivative using the quotient rule. And if you don't know how to do the quotient rule, my previous video covers that. So if we take this derivative by following the formula for the quotient rule, we have low cosine x, d high, derivative of the high, the numerator, sine x, minus high sine x, d low, derivative of the denominator, cosine x, all over the square of the bottom, cosine x. Low d high minus high d low, square the bottom. So that is how we set up the quotient rule of sine x over cosine x. Now if we follow the ddx's, we have cosine times the derivative of sine x, which is cosine x, minus sine times the derivative of cosine x. I'm going to open a bracket here so that our subtraction is clear. So we have sine x times the derivative of cosine x, which is negative sine x. And then that is all over cosine squared x. I just rewrote this by bringing the 2 above the cosine. If we simplify this, we have cosine squared x. This negative sign is going to distribute with this negative, so we're going to have plus sine squared x over cosine squared x. Now we can simplify this even further by using our trig identities. Specifically, the trig identity that says cosine squared x plus sine squared x equals 1. So we can rewrite this numerator as 1 over cosine squared x. And then 1 over cosine x is the same thing as secant x. So 1 over cosine squared x equals secant squared x. So the derivative of tangent x is equal to secant squared x. And instead of doing all of that math every time we want to take a derivative of tangent, we can just add that to our rules. That the derivative of tangent x equals secant squared x. So if we wanted to take the derivative of y equals tangent of 7x to the fourth, we take a derivative of both sides. We start by taking the derivative of tangents, which we added to our rules. The derivative of tangent x equals secant squared x. So we have dy dx equals secant squared. And now remember, we're following a chain rule, so we keep the inside the same. Secant squared 7x to the fourth, and then times the derivative of our inside function. So we're going to have 7 times 4x to the third. If we simplify that, we get dy dx equals 7 times 4 is 28. I'm going to bring that out to the front. 28x to the third times secant squared 7x to the fourth. I hope this video was helpful for beginning to take derivatives of trig functions. We covered derivatives of sine and cosine x, which we discovered is a repeating pattern. And then we took derivatives of trig functions to some power, which required us to apply the chain rule 3 times in some cases. We used the product rule to take the derivative of trig functions that are multiplied by each other. And then we used our quotient rule and our trig identities to take the derivative of tangent x. Thanks for watching. Like and subscribe for more math. There's still a lot of calculus to cover, and I hope you have a wonderful day.